Hey guys, welcome to Advent of Code 2022, day 16. Now, it's a few days removed from day 16. It took me a very long time to solve this puzzle. There are multiple cuts, multiple times I quit, went and thought about it, came back, and I recorded each time I came back. So I'm going to have some timestamps in the description, and you can click through to where you'd like to see. I go through three totally different solutions to try and solve this puzzle. My final solution only ended up taking 2 hours to run. So definitely some long running processes here. But yeah, if you guys are interested in watching me hem and haw for about 3 hours, feel free. This is the video for you. So thank you guys for watching. Like and subscribe if you enjoy it. And I'll see you next time. Peace. Welcome to Advent of Code 2022, day 16. We're getting into the tough ones now. I'm pretty excited to get started. Hope you guys are enjoying the videos. Let's get going. Proboscidea volcanium. The sensors have led you to the origin of the distress signal, yet another handheld device, just like the one the elves gave you. However, you don't see any elves around. Instead, the device is surrounded by elephants. They must have gotten lost in the tunnels, and one of the elephants apparently figured out how to turn on the distress signal. The ground rumbles again, much stronger this time. What kind of cave is this exactly? You scan the cave with your handheld device. It reports mostly igneous rock, some ash, pockets of pressurized gas, magma. This isn't just a cave, it's a volcano. You need to get the elephants out of here quickly. Your device estimates that you have 30 minutes before the volcano erupts, so you don't have time to go back the way you came in. You scan the cave for other options and discover a network of pipes and pressure release valves. You aren't sure how such a system got into the volcano, but you don't have time to complain. Your device produces a report or puzzle input of each valve's flow rate if it were opened in pressure per minute. The tunnels you could use to move between the valves. Okay. There's even a valve in the room you and the elephants are currently standing labeled AA. You estimated it'll take 1 minute to open a single valve and 1 minute to follow any tunnel from one valve to another. What is the most pressure you could release? Okay, I don't know if I fully understand it right now, but let's copy our inputs and read the example. Let's go here. I'm gonna go down and grab the puzzle input. Okay, all right. All of the valves begin closed. You start with valve AA, but it must be damaged or jammed or something because its flow rate is 0, so there's no point in opening it. However, you could spend 1 minute moving to valve BB and another minute opening it. Doing so would release pressure during the remaining 28 minutes at a flow rate of 13. The total eventual pressure release would be 28 minutes times 13 equals 364. Then you could spend your third minute moving to valve CC and your fourth minute opening it, providing an additional 26 minutes of flow rate of 2 or 52 total pressure. Making your way through the tunnels like this, you could probably open many or all the valves by the time 30 minutes have elapsed. However, you need to release as much pressure as possible, so you'll need to be methodical. All right, so this is an optimization problem. There's many ways to solve optimization problems. Sometimes you can just solve them by reading it, the way the problem is structured and knowing how to construct the optimal answer. Sometimes you have to evaluate many different strategies. So one strategy that comes to mind for this sort of problem is a recursive splitting strategy, or I believe it's some sort of dynamic programming. But anyway, you start with one solution, and if you come to a fork in the road, such as these tunnels lead, then you just evaluate all three options and then keep going. And I suspect that is what we will need to do here, is create a recursive forking strategy. Because but let's consider if we did a greedy strategy. That is a strategy where we always choose some heuristically better option and we never really evaluate other options. So consider AA leads to DD, II, and BB. BB is 13, DD has 20, II has 0. So if you walk to D, D, you get a rate of 20 at the highest multiplier. So that's optimal for the first option. But if you then continue on to CC or EE, then let's say you choose EE because it has 3, then you get to go to FF, which has 0, then you get to go to GG, which has 0, then you get to go to HH, which has 22. By the time you get to 22, it's much lower. Maybe it would have been more optimal to go to BB, which is 13, then CC, and then DD, right? And then you get back to this this route here where you release everything. So I think it's pretty clear that the optimal route is greedy in the example, but I don't know if it's greedy. Actually, I believe the optimal route is not greedy. Yes, all right, we found a counterexample. So the optimal route in the example is going to be DD, then back to CC, then back to BB. That way you get this 13 at a high rate. And then going out to the 22, right? I think that would be, yeah. So this is the, right. No valves are open, you open DD. DD is open, releasing 20 pressure. Then you move to BB, and it takes you 2 minutes to move to CC. You don't even open CC. You just skip it and move on. This is cool. Yeah. All right, so cool. All right, I think we're gonna do this recursive strategy. All right, so let's parse our input. It's gonna be a little bit tricky. So we have data class valve, has a name, string, a flow rate, int, we'll just call it a rate, and tunnels is a list of valve. And then we're going to track open state, but we're going to do it outside of the class valve because I don't want to have any mutability. So we're going to have data class valve state, and this is going to contain a map of open equals is a dict of string to bool. Yep, and then we're going to have a total flow, which is an int. So that valve state, we're going to pass this around and update it. So this starts as empty, and this starts as 0. And we're going to add some functions to this. So this will be our nice little, it doesn't even need to be a data class. Cool. All right, so let's parse our input. We have valves here. And valves, parse valve. Or how about we just do valve.parse. We do that static method, def parse, line stir, valve, and then return valve name. I guess we got to split on strings, so we're going to do underscore name underscore rate stir underscore star tunnels stir equals line.split on string. All right, or on the space. So then we just do, all right, so name is name, that's going to be the same. Rate equals rate and we want to index at the 0, 1, 2, 3, 4, 5 to -1 and cast that to an int, and that'll give us the rate. And the tunnel stir, we want to do tunnels. I guess it's going to be a list of names. Tunnels equals tunnels stir dot split on comma space, and that should give us all the tunnels. Okay, that'll be nice. Cool. And valves equals dict stir to valve. Cool. All right. So yeah, we have the input, we have the valve state. So let's do state. Let's initialize our state. Actually, we're going to create a helper function for part 1. So we're going to do def optimize escape. Or we'll just call it escape. Fuck it, right? Sorry for cursing. So we're going to def escape, and we're going to have a state is a valve state. And this will return an int recursively. All right, so let's think about this. First, let's go state equals valve state input and return state escape state. Oh, and we should pass a time. Oh, yeah, we should have a time. The time is incrementing. We'll just have time left, right? Yeah. Time left is an int, and it starts at 30. Okay, so if state.time left is 0, return state.total flow, right? So our answer is total pressure. And every time we escape, we need to increment the time left. So if the time left is already 0, we just exit. So otherwise, we want to decrement the state. So if we want to update the hold on a second. We want a copy function. Whoops. Sorry. So if we copy this, return valve state. Okay, this should work. So when we escape, we first want to copy. So state, let's consider our cases first, and then we'll handle everything else later. So what are the things we can do? We can either open the current valve. So if Oh, we have a location, right? Yeah, we have a location. Location is stir. This equals AA at the beginning. If state dot location in not in state dot open and state dot valves state dot location property. All right, so also I'm moving escape to be a method on this, on the valve state. Okay. And we'll just change state to be self. All right, so if self dot is open, self.location, and we want to do not, if it's not open and it has a flow, and self.current valve dot flow rate is greater than 0, then we want to evaluate as evaluate opening current valve. I'm rethinking this. I'm thinking that we want to have this do a single iteration. So I called it escape 1, and it's going to return a list of new valve states. Yeah. Okay, so our options of start out as an empty list. So if we evaluate opening the current valve, so options plus equal, so new open state equals state dot self dot copy, and open state dot open self.location equals true. So now we've opened another valve. Then now we're going to call open state dot open state. Now we're going to add open state to our options list. All right, and then we want to check out going to different moving to different valves. So we can move to every valve available. In fact, we can go out to a valve and then come back. So we have to evaluate every option. So for tunnel in self.current valve.tunnels, evaluate going to that tunnel. Go state equals self.copy. Go state.location equals tunnel options plus equals go state. All right, so now we've evaluated all the options in a single. So the last thing we want to do is we want to iterate the time left and total flow. So for state in options, state.iterate, I'm going to have a little function here called iterate, def iterate self, which will do time left, self.time left minus equals 1, self.total flow plus equals the open should be a set. It doesn't need to be a bool. And self.valve. Valve in self.open and self.open.add. When we copy, we can do this. So we can just do open equals optional location and move optional stir equals none equals none. So location equals move or location and self.open .union open if open, else none. All right, so that's just a little bit of small needless optimization, but if you've been watching my videos, you know I love to clean up code and make it a little cleaner. That way it's easy to reason about. So when we do these copies, we can do open equals self.location, and then we can do this. And self.copy move equals tunnel. And actually when we copy, we can iterate, right? We can call copy iterate, and we can do time left minus 1 and total flow new open equals this. Whoops. If open else self.open, and then we do new flow equals sum of valve self.valves v dot rate for v in new open. Okay, so then open equals new open, total flow equals new self.total flow plus new flow. And that is our iterate function and our copy function in one, since we do them. So we just call self.iterate. Cool, and now we return options. All right, so now we have a list of escapes. And we actually, so and yeah, so for I in range 30, so 30 steps, states equals state for state in as for s in state dot iterate dot escape one for state in states. So this is a little double for like a flattening, essentially, of calling for each state we want to escape. That returns a list of states, and we want to flat map that. So this is like a monadic bind, if you're familiar with that. And we just do it for 30 states, and then we order them. And we do return state max of state dot total flow for state in states. And that should work for part one. Valve state not defined. Mutable class dict for field open not allowed. Use default factory. Data classes. Okay. All right. I guess the data class part of this isn't working super well. So let's do. Let's just define our own init function. It'll take a second. Def init self valves open total flow time left location self.valves. Yeah, I know it's not typed, but it's quick enough and it'll work. All right, rate is not defined. Did you mean to use range? Rate stir. List object has no attribute split. Ah, yes. Okay. Valve state init got unexpected keyword valves. I guess you can't have two inits, right? So that static method def from input actually, fuck, let's just move this. I'm just gonna back up a bit, move this around, okay, and just use this. And open starts as empty array. Total flow is 0. Time left is 30, which we don't actually need anymore, because we're measuring time outside. And location is AA. And that's good. Missing one required positional argument input. Valve state has no attribute time left. Dict object has no attribute union. dict object has no attribute union. Okay, we're actually running. But it's taking too long, so maybe we got to be smarter about it. But I'm going to do what I did last time, import tqdm, and okay, so we're quickly bubbling up into millions of states. So let's think about this. How many variables actually determine the amount of states? Valves doesn't change. Open does change. Total flow changes, but if you had two things that were otherwise equivalent, you could eliminate the lower total flows, right? And the location. So I'm thinking of a way to optimize this is to reduce the set of states that we have. So after we expand the set of states, then we go ahead and we merge them with each other. So to do this, the one trick I'm thinking of is like, okay, so we take the set of open states and our current location and we create a key with that. And we merge anything with the same key. The way we merge it is we choose the one with the best total flow. But that could be erroneous if, is it ever possible, I guess the question is, for something with less current total flow to have more eventual total flow? And I think the answer, with the same open and location valve, I think the answer is no. But I'm a little worried that I'm not thinking of something. So I'm gonna go back on ourselves. I'm gonna add back our time left. And what I'm gonna do is when we iterate, we're gonna add the flow until the end of the time left. So we're never in a case where future flow might grow past current flow. We're always just gonna have eventual total flow calculated. And this way, when we merge things, we can just use total flow as an ordering function. So the new flow now is self dot time left minus 1 times self dot valves of the one you're opening. We only calculate when you open it, dot rate. And that is only if we're opening something. If open, else 0. And this way we add all the flow. So when we open, in this example, when we open D, right now we're going to calculate 20 times 28 and add it. And we don't have to add 20 every time. Okay, so now we need to create a merge function, def merge, or key, self, and what we're going to do is create this is a tuple. Are sets orderable or sets hashable? hold on a second. All right. Set 1, 2, 3. Can this be used as a dictionary key? Unhashable type set. So we can't use a set as a hashable type. So we need to create a hashable type. So we need to have our, wait, can we just make valve state hashable? Python hashable. I'm not going to worry about it. So what we can do is have a list, or a list is hashable, right? No, lists are not hashable. Tuples are hashable. Strings are hashable too. So what I want to do is create a string that represents the valve state based on the open set and the current location. So I'm going to return a key as a string. Return self.location. Format string. And we're just going to do colon. And then plus comma dot join t if v.name in self.open, or if self.isOpen v.name for v in self.valves. And actually we don't even need a comma here. All right, so now we have a key that represents our current location and open state. And so what we're gonna do is def at static method def merge self, there's no self, sorry, states valve state. So we're going to take a list of valve states and we're going to merge them. So first thing we want to do is put them all into a dictionary. So this is a group by function. So itertools has a group by function. Group by. So we're going to do groups equals group by states, and the key equals lambda ss.key to return this key. And then we want to do, and then for each group, for key, we don't really care about the key, and group in. For each of these, we want to take the max by. So Python max by. Oh, I don't want to click that. Yes, there's a key function on max. Okay. So return max of group, the key equals lambda state s dot total flow. And this will give us the maximum, the state that has the total flow for every state that has the exact same key, which is every state that has the exact same open and location set and current. And since everything is guaranteed to have the same time left, then we're all good. So now we need to do valve state.merge. And now we need to run. Didn't import group by from itertools import group by. Stir has no attribute name. Right, it's good. Okay, we're still expanding. We shouldn't have this many states. Okay, we didn't expand as much. We got to 6 million in iteration 14. Iteration 14 only had 474,000. Okay, so that's not cool. Clearly merge didn't do enough. Let's double check we did it correctly. Is it ever good to go backwards? I mean, I think it can be, right? Like, maybe not a lot. All right, so this is clearly a graph traversal function. So maybe we should be representing things as a graph. Well, you guys have been watching me for a bit now, and I'm a little bit stumped on this one. I think what I'm going to do is close the video for now and think about this problem and then come back to it. I'll probably record later tonight and have some more intuition, you know. We either need to create a better optimization. Maybe there's a bug in here and we need to fix it. Or our method is just faulty and will just take way too long to run. We can't really have that many outcomes. Well, I mean, in the example, there's only 6 valves that can open. And there's only, so that's 2 to the 6. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 times 2 to the 6. Which is only 640. There should only be 640 keys. All right, so this whole getting up, so there must be a bug. All right, good. All right, we're good. Because, we're not gonna open anything with rate 0. So there's only, so we just print all right, there must be a bug. All right, and I'm only gonna run to like level 6 so I can read this output. All right, here we go. Here's a problem. You shouldn't have two of these in your states. They should be merged. How do you continue? Okay. There are multiple states that are the exact same here. So, merged. All right, we BB and BB the same key. So why didn't they get merged? All right, maybe group by just doesn't work. So we're just gonna do best is a list and for state in states, best of state.key equals best.get state.key. If best.get, if state.total flow is greater than best.get.state.key, total flow, best state.key equals state. State.key in best and key equals state.key. Just a little, just writing this out. This is just way more, obviously it's not as pretty than using group by, but I don't know, something about group by isn't working. Probably my understanding, not group by, but that's okay. Not in or this, and then return list best.values. Okay, much better. Our merging actually works. All right, returning this and running until 30. All right, we actually get, and we only ever get up to 320 states as a maximum value on states. And did we get the correct answer? We did. Okay, all right. I was almost gonna quit there, but we did get it done, and we can run the full answer here. Is gonna finish momentarily. And we get up into 132,000 states, 163,000 states in the full answer. Submit it and we get it right. So I'm glad we didn't quit. I'm glad I kept pushing and thought about it some more. I thought that this optimization was really pretty good. It's basically, you flat map and then you merge. And that's a pretty classic pattern in some of these. You're worried, part 2, you're worried that even with an optimal approach, the pressure release won't be enough. What if you get one of the elephants to help you? It would take 4 minutes to teach an elephant to open the right valves in the right order, leaving you with only 26 minutes to actually execute your plan. Would having 2 of you work together be better, even if it means having less time? Assuming you teach the elephant before opening any valves yourself, giving you both the same full 26 minutes. Okay. So now there's a larger set of states, but we only have to go to 26 minutes. Okay, cool. So yeah, what do we have to do? You basically move independently, right? So actually what we have is, all right, we're gonna have to, I'm just gonna copy all of this. Well, we can keep some things. So let's just do class valve state 2 based on valve state. We still have valves and we still have self.open. That's still the same. But, and here I'm just gonna have 2 windows here showing valve state. But what changed? Total flow is still going to be the same. Time left is still the same, although it's going to start at 26. Location is now going to be a pair. So, so now we have locations, tuple, stir, stir. You know, and this is going to start out at AA. We definitely need a new iterate function. And since 2 things can happen at once, right? The elephant can do something and you're going to do something. We want to do elephant open. You know, actually we can make an action, class action. Doesn't matter. We'll just write it like this. Ideally, you'd use like an actions class or object here. And you have an elephant action and a person action, right? So, well, let's just do it. Class action. Open optional stir equals none. Move optional stir equals none. We'll make this a data class. And then we'll do me action elephant action. And this is going to return a new valve state 2. All right, so the new open is the union of we'll just do me.open elephant.open v for v in this if v. All right, so this will just give us if either of us open new things, then we union it, right? And then actually let's take this list and we this needs to be colon opening. All right, and then we want to do opening here, and we do self.timeleft times O for O in opening, and we do sum on this. There we go. Okay, so now we have our new flow, so this is all good. And then the location here needs to change to locations, or actually, well, so location, or overriding location, and it'll be me.move if me.move else self.location 0, and elephant.move if elephant.move else self.location 1. Cool. All right, so we now have changed our iterate. What else do we need to change? init needs to change to, well, actually, init doesn't need to change. It's the same init works because we're keeping the same key. Cool. From input needs to change because valve state 2 needs to set time left to 26, and our locations start at AA. Nice. And cool. So then current valve doesn't really work, but we're just gonna ignore it. Is open, still works. Escape 1 will obviously need to change, and that is the major thing here. We'll call it escape 2. Hell yeah. And I'm not gonna worry about it for now because I'm gonna modify the key. Now merge still works, which is awesome, but the key needs to change. Actually, the key doesn't need to change because self.location will still map to a string fine. Okay, so we should be good. And actually part 2's, so now we can just focus on, I'm gonna remaximize this, and now we can focus on escape 2 and what happens in it. So if is open, right, we need to do both what I do and what the elephant does. So the difficulty here is like, what if we both want to open this? What if we're in the same location? Then we can't both open the valve. But the good news is that's just one case. So let's do if we're in the same location. If self.location, let's make property def my location self turn self.location 0. And the same thing for elephant. Nice. If self.myLocation equals self.elephant location, then we have a special thing where only one of us can open the valve and then the other one has to move. So first of all, if is opening the valve even possible, then if it is, then we go through each tunnel for tunnel in self.currentValve.tunnels. Yeah, let's do def my current valve self return self.valves self.myLocation. All right. All right, so if my valve is worth opening and it's not currently open, then we're gonna go through each tunnel and add to the options self.iterate with me at action open self.location. And elephant equals action move equals self.move equals tunnel. And then we're also going to do the same thing, but what if the elephant did it? Wait, are those equivalent? They are equivalent. It doesn't matter who is where, which implies two things, right? First of all, we don't need to put two cases in here. We don't need to have me opening and the elephant opening as two different cases because they're equivalent. The second thing is that we can copy this key function and we can optimize the key. We can reduce the key space by not caring which one of us is in which location. We can do sorted location equals self.location list sorted. So self.location is a tuple, but if we sort it, it doesn't matter who is where because it's totally equivalent. So the key space is now slightly smaller, and this should help keep everything down. Awesome, good intuition here. Okay. So if so now we have if the current valve where we're at, if we're in the same location in the current valve where we're at is not openable, well, it doesn't matter. But now we have to like go through each tunnel and move us to either tunnel. So this is like a two-step thing. Right, so we can move to either tunnel. Does it ever make sense to move down the same tunnel? Sure, there could be a case where the highest things are both down the same path, so we need to handle it. All right, so then now we do else. Here. All right, and if self.my current valve It's just a lot of cases here to handle, so I'm just going to go through and do them all. So actually, all we need to do is list out the possible actions of both of us, and then we can, this will be so much simpler. All right, my actions list action elephant actions equals list action equals this, colon equals this, and then we'll do this at the end. We do if I can open my current val, then my actions plus equals action open equals self.location. And for tunnel in my current vals, my actions plus equals action move equals tunnel. And then we do the same thing, but for elephant. Okay, nice. Cool, okay, all right. So now we have a list of all our actions, and then options equals self.iterate me equals me, elephant equals elephant. For me in my actions, for elephant in elephant actions. And the only thing we'd want to prevent is if we're opening the same valve at the same time, because we know that that's just can't be done. So if me dot open and me dot open equals elephant dot open, or if not this case. And then that should iterate on everything, and we return that. And yeah, this is really good. Sorry, I'm cursing. I do curse. I apologize. Okay, and we want to do the same thing, but we're only going 26. And we're using valve state 2 and valve state 2.merge. And we're using escape 2. Cool. Let's try it. This got to return valve state 2. Valve state 2. 1707. Ah, yeah, we did it. Nice. Input. Let's go. We did it, dance. Wait, why are we doing so many iterations? Oh, it's rerunning part 1. I always do that. Short circuit that. I expect this to finish. Okay, we're growing. Let's think about this, right? Like, how many states are there? For the input, how many lines are there? 58 lines. So for part 1, we had 58 times 2. Well, how many of those don't have rate 0? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Only 14. So we've 58 times 2 to the 14. So that's a possible 1 million states. It's not too many, but what we have now is 58 times 57. So now we're up to 50 million states. And as you can see, we're already up to 6 million on iteration 14. So this is going to take a bit of time. Could we use another heuristic to optimize this? Or should we just wait? Well, we know that from part 1, we know what the optimal route is for one person. But you can't just use that route because as a, like if your route goes and opens 20 rate and then goes and opens 18 rate, why couldn't the elephant just go open 18 rate and more faster? And so that's not really good. So in this case, they have the elephant opening DD, just 20 pressure, while you walk all the way to JJ, which takes you 2 minutes. And DD and JJ are the highest producing pressure. And then you walk, then both of you move a lot. I guess you could do like some sort of heuristic, but it'd be kind of a guess. Where are we at? All right, we're down to a minute per iteration. This is getting upwards to, we're only at 1.8 million, so we can still grow 50 million, which means, the final iterations could take maybe upwards of an hour, which would be bad. Right now, we're doing 30 seconds per iteration, and that is growing at a rate of 2. So we have 10 more iterations to go. And how long is that going to take? So 30 at x equals 30 for I in range 10, x times equals 2. That will eventually take 8.5 hours to run the final iteration. So that'd be bad. Although at some point the merging will occur and keep it limited. I think this will only take maybe an hour to run. But who knows? Let's think if we can do any more optimizations before we give up. Okay, I have a thought. Instead of modeling each iteration in a single function, what if we did more than one iteration in a single, more than one time step in a single iteration? So for example, what is the first thing we do in this example? The elephant moves to DD and opens DD. That takes 2 time steps. And in fact, what we are looking at here is a list of plans. DD and JJ, then moving to BB and HH. So if we think about this, optimal planning. And CC. And that's your plan, and the elephant does what? The elephant opens DD. Oh, sorry. Yeah, I don't think this is going to run well enough. So what if we think of it as planning? How many possible plans are there? Really not that many. And so I can take a plan. I can make a function that takes a plan and calculates how much flow it will create. And I can make a function, and I can measure the distance between each valve to help that. That's fast. And then the question is, how many possible plans are there? If there's only 14 valves that can be opened in the full input, then that's maybe like 14 times 13 times 12. That's not that many. And for an elephant, so you just do that times 11 times 10 times. It's still like on the order of 10 to the 6, which is about 1 million, which isn't that bad. So I think this is definitely doable, and clearly this is not going to work. So let's rewrite with a planning. The first thing we need to do to change everything is to create a map, a graph, and measure the distance between each valve. And we actually only care about the distance between valve AA and any valve with actual flow. So how do we measure distance between valves? We need a graph algorithm. Graph distance to all nodes. Shortest distance between all pairs of nodes in a graph. Oh, geez. I think we can just do a shortest. So def shortest paths valves. And this will return a dictionary of tuple of name to name with an int of how long it takes to get there. So for valve in valves. So for each valve, we're going to do the shortest path from. So our paths are dictionary of tuple of valve dot name to, we'll call this for fro. We'll do fro dot name to dot name, and we'll do just 1,000. It's never going to take that long. For to in valves. And a pass of fro.name equals 0. And then for tunnel in, and then we go, then we just need to depth first search. I don't know. All right, I'm gonna cut this short. It's getting way too long. It's never gonna really reach the end, so we're gonna start on this new. So I wrote a shortest path algorithm. It's just O of n cubed, but it's really not that much. So we're just gonna test it out. So paths equal shortest paths, input.valves. Oops, I'm gonna have to close this buffer. Okay. This must be running infinitely. All right, so we're staying at AA just forever. Oh, right. Okay. Okay, we made a shortest path graph. So let's just test it. EE to JJ in the example. EE to JJ goes FG, no, EE's got to go to D, B, A, he's got to go I. The only way to get to JJ is go through I. So from E is to go to D, which is 1. And D is to go to B. So D has to go to A, which is 2. And then from A, it goes to I, which is 3. And from I, it goes to J, which is 4. So yeah, that's correct. All right, so we have a shortest path algorithm. Cool. And then we have plans. So we need to see if a plan is feasible. So given our paths, is plan feasible? Plan is a list of stir, and we have our paths. And we basically just want to add up the shortest paths between each set, and are they less than 26? Return sum of paths pair for pair in zip plan 1 : less than 26, or we'll do total time 26 total time. Okay, so that's if a plan is feasible. And then we need a function def plan score, which will just sum the time left. So let's do this. Sum equals 0 for valve. We want to do a valve lookup. So valve lookup equals v.name v for vn input.valves, and then for valve in plan time equals 26. We'll do time minus equals, so all plans start with AA, right? Let's just make that the case. Let's make all plans start with AA. And so the sum of the paths always starts with AA, and then time minus equals paths. We'll call this distances. Distances of last valve to valve, and sum plus equals time times lookup valve dot rate, and last valve equals valve, return sum. So now we have a planned score. And let's start by scoring the example answer. We had it, we put it here. Okay. So they're both feasible and they both produce scores, and the total score is not accurate. So do we do it right? So BB, CC, DD, EE, HH, and JJ. All right, so we do, that is correct. Oh, there needs to be, you need to -1 for the actual opening of the valve. Time, oh, this is +1, sorry. 1707, not correct. So for each valve that you traverse to, you subtract the distance you traverse to it, and then 1 minute to open it. You add to your score the time left plus that valve's rate. That all works. And then you go to the next valve, you travel to it, you add 1 to open it, and then you sum the score. This all seems pretty good. So let's just do this. Let's do print travel from last valve to valve in distances last valve and open with rate lookup valve dot rate for score time times lookup valve dot rate. All right, travel from AA to JJ in 2 with open rate 21 for score 483. So scrolling down, sorry. You move to JJ, you move to II, then you move to JJ, then you open JJ. So the travel distance is 2, and you open with rate 21. Then you travel from JJ to BB, so 1, 2, 3, plus 1. time left 23, time left 19, time left 17. No, we're not counting enough time. You travel from BB to CC in 1 and open with rate 2 at time 17. Time left 17. That doesn't make oh yeah, time left 17. Because we're only on minute 9. There are 17 minutes left. So you get 17 times 2. So yeah, and for the elephant, it opens DD on turn 2 and has time left 24 for a score of 480. So that's because 20 is open from minute 3 to minute 26, which is 24 minutes. So that's correct. Okay. DD is open at turn 2. Wait, wait, hold on a second. What? Oh, right, because we're calling it twice. Okay, that's fine. All right, so DD is open at turn 2. Then JJ is open on turn 3. And then the next thing is turn 7. Both BB and HH are open. Yep, that's what happens. And then turn 9, you open CC. Yes. And at turn 10, turn 11, the elephant opens EE. At this point, all valves are open. All right, so that should be the accurate score. Oh, it is the accurate score. Oh my gosh. Last 10 minutes I've been debugging something that is correct. All right. All right. I think we're ready to write the final piece of this puzzle, which is all possible plans. So all plans. That's basically every. So first we need valves with pressure, pressurized valves equals v.name for v in valves if v.rate is greater than 0. And now we just need to go through every single possibility, filter them for the ones that are feasible, and then run the plan score on all of them. So a plan is a tuple of the two lists that both start with AA, and so plans equals, and we're going to make a generator here. So it's a generator of a tuple of a list of string and a list of string. So for each, we have AA plus we're going to make a def plans for valve in pressurized valves. So there's 14 possible valves. So first, let's make single plans, right? A plan for a single person. We need all possible single plans. And we need to do it given a set of valves. So that's just every combination, every order of this list, right? Every select, so there's an iter tools for that. All right, permutations, all possible orderings, no repeated elements, are length tuples. This is what we need. So for len in length in len of p valves, sorry, range 1 to the len of p valves plus 1 for plan in permutations of p valves with length yield starting at AA plus the plan. This will give us all possible single plans. And then we're going to do if is plan feasible P yield P. All right, so then now possible single plans. And then def second plan given a plan will give us second possible plans. So p-val, which just all we have to do is return single plans of pressurized Cool, so the second plan, right? And then def all plans is the generator of this tuple is for plan in single plans pressurized valves for plan 1 in single plan, for plan 2 in second plan 1 yield plan 1 plan 2. And then all we have to do is plan score. So we do return max plan score of P1 plus plan score of P2 for P1, P2 in all plans. This is fun. Day 6, line v done in 0 input dot valves. It's just a typing error. Oh yeah, generator doesn't. We're just gonna get rid of the types on generators because I don't know how to type them right now, and I don't really want to learn right now. But you guys get it. Permutations not defined. Stir has no attribute name. Oh my gosh, that was fast. Let's see how long it takes to do this input. I wonder, I mean, I think this is the right solution. But with 14 choices, you know, that's testing 14 factorial and all possible permutations. It's a lot. Six permutations was not so bad, but 14's also just too many. Can we Well, this has been a long video so far. I've tried 2 solutions, both of which I've optimized somewhat. I think at this point I'm gonna end the video and maybe pick it up when this completes, or maybe if it doesn't, we'll see. But I appreciate you guys for watching. This is just my real process. This is how I'm doing it. And yeah, thanks for watching. I'll see you guys next time or at the completion of this video. Peace. Hi, and welcome back to Advent of Code 2022, day 16. We are still not done. I left my plan-based solution running all day, and it still is not completed, so we're just going to kill it. And pretty much, I don't know, in the 5-10 minutes after I cut off the video, had to go to work, I was thinking about this problem, and I think a greedy solution can be really good. And I think we can either take a fully greedy solution, that's what we'll try first, and we'll submit the greedy answer, and we'll construct it like manually. And then hopefully if that doesn't work, we'll come up with a really good way to construct a smaller subset of plans to validate and maximize. So the first thing I want to do is I just want to start with what is the graph. So I'm going to scroll all the way down. There's a lot of code here. So we've tried a lot of different things. And we're part 2. Okay. So I'm gonna just import IPDB, and IPDB does set trace. Go right here, run it on our input. Pip install IPDB. Why do I have to do that every time? I don't know why it's not just always installed. Okay. Whoops. So let's take a look at this. Let's look at our distances array. Okay, so we have 58 different nodes, but you know what really matters? Only the distances between nodes that have rate or the first node. So let's do KV4 KB in distances dot items if K0 in pressurized and K1 in pressurized valves. I don't know, something about this debugger. Okay, well, I guess we'll put that here. Okay, distances. Okay. This is small. Yeah, this is smaller. And we don't actually need the distances to the same node. That's an interesting thing. So we can remove those and K0 not equal K1. Okay, so we can print out all these. We have all of them. Okay, so now I want to write a function that considers a state and picks the next greedy solution. So they have pick greedy solution, and it's going to take in a current set of plans and pick the next best plan. So plans, which is a tuple of list of string, list string, and returns that same plan equals this. And if, so basically we want to, so this is actually really good. Okay, so we have our pressurized valves. I'm gonna move, so when we have our pressurized distances, and then we're gonna print, and then the starting plan is both plans starting at AA. Okay. So, me time, so the time that we're in on the first plan is plan 0, which is basically this sum feasible thing. So def plan time and then is plan feasible is plan time plan less than total time. Okay. So we take our plan time, so that's nice, and elephant time is plan time. Actually, we'll do okay, so we get the me time and the elephant time, right? And so the greedy solution is going to pick the next best choice for the one of us that is lowest in time, or sorry, because that means there's more time left to get to the like highest nodes. So if me time is less than or equal to L time, then pick for me. Okay. So now that we know which plan we're going to pick, so we're going to do return pick greedy solution plan for plan list stir and then we need to know available valves equals set pressurized valves dot sub dot minus dot difference on plan 0 dot difference for plan 1, or we can just plan 0 plus plan 1. Okay. So now we have the available valves, and we take 0 and available valves. All right, now we just need to write this function. these are the valves to choose from, and it is a list of string. Or it's a set, doesn't really matter. We're going to return a plan. Okay, so how do we pick the next best plan for the set of valves? Is we need to go for each valve. We need to take how much score, how much time it'll take to get there from our current time times how much time will be left once we open that valve times its rate. So the plan is also includes the current time left. So we take, and we have starting time is 26, so we have total time here. So time left equals plan time on plan, total time minus plan time. Okay? And so the available valves, the valve scores equals input dot, or lookup, I believe is what I called it, lookup valve dot rate times time left minus 1 to open it, and then minus how much time it'll take to get there, distance. And that distance is pressurized distances of plan -1, of the pair of plan -1, the last thing in plan, to the valve we're talking about. All right, so let's put this on a new line. So we have the rate times the time left minus how much time it'll take to get there. Okay. That's the valve score. And we want a pair of that with the valve itself. For valve in valves. So each valve score, so then we just pick the best. And so we return max of valve scores 1, which gives us the valve. So, or actually we need to return a plan. So pick valve equals max of valve scores 1, and then return plan plus pick valve. Awesome. So yeah, we should be good to go, because when you maximize based on a tuple, it maximizes the first value, so we can maximize based on this. Pick the valve. Okay, awesome. So we're picking a greedy solution. Awesome. So what we want to do is pick the greediest solution. And so we want to filter this for valves that we can get to. If it's greater than 0. If you can open it before 0 time. And then if valve scores is empty, or if it's full, do this. Return else, return none. So new me plan equals resolution plan. I still think we're gonna have to do a recursive thing in here, but I don't think this will be the right answer, but it'll give us a good, and we've already gone over 2 hours and been all day, so we might as well just do this right. So new me plan, if new me plan, return this, else. Then if you can't pick a new me plan, then you try to pick. Actually, we should just do both. No, we shouldn't do both. Then new L plan equals this. If new L plan return plan 0 new L plan. Yeah, and if you can't pick a greedy solution, then you just return false, right? So that is how we do it. So we're gonna do this, and this, and this, and this. And this is not clean, but cool. All right, and now I want to keep going equals true while keep going starting plan plans equals starting plan plans keep going equals pick greedy solution plans if not keep going print final plans print and return plan score plan for plan in plans sum of those guys. We'll remove all this and plan is not defined. I keep seeing this. This is this, is this, is this, is this, is this, is this. Did I miss any? I did not. Okay, so this is the greedy solution. And it will not be the right answer, but I'm going to try it because it's the first answer I've gotten, and it is too low, of course. That is what we expected. That's good. It means, but this greedy solution helps us be able to pick. So I think what I'm going to do is merge what my last tactic was with this tactic, where I generated all possible plans and then filtered them for feasibility. And then I chose, okay, well, let's just pick what appears to be the best plan, which is not the best plan, but it appears to be at each step. Now let's merge those. Let's use what we've learned from picking a greedy plan to generate all possible good looking plans and then maximize them. So finally gonna write some more stuff here. Def all smart plans starting plan plans equals and this will return a generator of all plans, but I'm not going to write that because we don't know how to write generators. Okay. So when we're picking a greedy solution. So let's just start by right, so we have basically a solution here. This gives us all our valve scores. The way we want to do this is we just want to get every possible valve. So instead of pick greedy solution, we want all solutions, all next plans, all next plans. So this will pick the next plan for starting with picking the next plan for me and then elephant. But just for the first round, we don't care. So we say if plan 0 is equal to plan 1, plans 1, then first round, just pick for me. And then we do all next plan P1 plans 1 for P1 in all next plan of P plan 1 with available no valves as all available pressurized valves. Okay. Else, then we do pick me equals the same thing. Pick elephant is very similar but different, where we take plans, where we pick a next plan for P2, P2 and all next plan P1. So this is P0, this is P0. And in these cases, we want the set of pressurized valves that are available. I haven't set up multi-select in Emacs yet, so this would have been better. Okay. And then we return pick me plus pick L. Right? And this should, and then we basically want to iterate this until, well, all right, so let's write all next plan. Just similar to our inner, this takes a plan and available valves. And returns list of plan. And this is just super similar to this, but without the scoring part even, right? So we calculate the time left and we run the valve scores, and we don't even need the score. We just need the valve. And then we return plan plus valve for valve in valves left. Cool. So now we have all the next plans. Cool. And then we're just going to like generate all these, right? And we can change everything to a generator. But let's just keep it as a list for now. I don't know. Let's make it a generator. There is an itertools function, right? To chain. So we can just return chain. And import chain. Wow. Written a lot of code for this thing. Let's see if we can finally get it right. Okay. All next plans. Right. And then when do we escape, right? When do we know that we're done? We know we're done when all next plans doesn't change. So let's have a function that calculates if a plan is complete. Def is plan complete. So we take the time left. And we only care about the max time left. And then we take the valves left, so return any of this condition. Oh, but we need to know which plan has time left. Oh, yeah. Me time left. So let's start with this plan complete, and its plans complete is obvious. Okay, so all right, we gotta split everything. This is just complicated with two plans here. All right, and then any time after for valve in pressurized valves, in set of pressurized valves. Okay, so if any of the valves are reachable from where we currently are at the end of our plan, given the time that we have left from the available valves, and then def is plans complete, plans, bool. We take the available valves, and we return is plan complete, plans 0 available valves. And we need both to be complete for both the plans to be complete. So we need to do this. All for plan and plans. Okay, so now we have a question of is plans complete. So now we can create some sort of recursive plan creator. All right. Def plans generator. All right. If is plans complete, plans, return plans. Or just yield plans. Else, then we need to calculate all next for plans in all, for sub plans in all next plans yield sub plans. Or we can just return all next plans, since that returns a generator. Okay, so now we can go back to our original that's our greedy solution, but now we need to go back to our original solution. So return max plans generator key equals plan score. Actually, when the plan is complete, we should just plan should just yield the score, right? Best plan is this, plan score, plans, and the plan score, I think we gotta write that. Down here, code is crazy. Return plan score plans 0 plus plans score plans 1. Okay. We have the best plan, return print best plan, return plans score best plan. Wow, okay. Plans generator. All right, so I'm hoping this will generate way less plans than our like permutations. Okay, didn't work. Wait, okay, so hold on a second. Is plans complete plans? True? That's not true. Is plan complete plan? Actually, let's do this. Copy this piece of code. Step. Available valves. Yeah, that's what it is. There's 6 valves in the Okay. So step, step. So time left is 26. Yeah, that makes sense, right? All right, so this is returning true. So the question is any time left minus greater than 0? So two. Time 26 minus 1 minus 2 greater than 0. Yes, that should be returned true. Oh, okay, yeah, it's definitely opposite. So we want all less than or equal to. So, and we also need to handle len available vals equals 0 or this condition. Okay. That should fix that. Plan is not defined. All next plan. Valve is not defined. All next plan. Max arg is an empty sequence. That's not good. Oh, right. Ooh, okay. Or sub plans 1. Sub plans in plans generator yield sub plans. Plan is not defined. All next plan 0. At least we're getting farther into this thing. Hey, we got the right answer for the example. Let's see, how long does it take to run on the input? Could run forever. I mean, okay, yeah, I mean, it's going through a lot of plans. I mean, there's 14 things, and when we chose a greedy solution, if we scroll up to our greed, we only picked 5, and well, there's 4 nodes here and 5 nodes here. So we picked 9 out of 14. So it's basically 14 choose 9. That's only 2,000. Oh, but then you have permutations of 9. So that's times 9 factorial. That's a lot. 700 million. All right, so we need an even smarter way to do this. How about we order our choices by what's best. Like we do a depth first search, right? And then we just cut it off early. What was the number we submitted before? 18 something? 1818. Oh, here we go. 2125. That's pretty good. All right, so while this is working, we can think of better solutions using depth first search, right? Oh, 22320. So with depth first search, we can mix our greedy heuristic with our not so greedy. How many items are we at? It's hard to read. It's moving. 1, 2, 3, 4. We're at 6 million. When are we going to get to 700 million? It's not going to take a while, I guess. I mean, if we're just submitting answers, still not the right answer. So still going higher. Well, at least, all right, so if we suppose that there are 100 million possible solutions, and in 2 minutes we've done 10 million, it will only take 140 minutes. That's only 2 hours. I can wait 2 more hours. It's already been all day. In the meantime, I can either quit again, take a break, or we can think about would depth first search help us, right? So what we can do with depth first search is we can use depth first search to create our plans. So this is basically a breadth of plans, right? We're looking at all possible plans and constructing all possible plans. Like when you're guessing phone numbers and you start with 0000, then 0001. Whereas with depth first search, you dive all the way down one route. But we can use the heuristic to choose which route we go down. So what we can do is create a second plan generator. Which greedy plan generator? Greedy plans generator. And it basically picks the next best plan. So it takes all next plans. All next plans equals next equals all next plans. And it just orders them by best. Right? So then Really, this is just all next plan sorted. This might be good enough. I kind of don't want to stop that one. Maybe we can create a separate process. Might slow this one down, but maybe we get to it faster. So let's just try. Okay, that is just as slow, I think. We got to 1926 pretty quick, right? No, it actually took us quite a while to get up that high. Yeah, maybe we'll just let both of these run. Wait, where did the other one go? Okay. Oh, one of these is a hotkey, one of them isn't. Two, 4, 8, 4. All right. You can tell I'm a little frustrated with this problem. I don't understand the trick. Still haven't looked up any solutions. Oh, that sort would have sorted in the opposite order, right? Okay, all right. Let's try it. Okay, what I've done here is I've essentially did the same thing we did before with the all next plan sorted. Actually, that all next plan sorted is ruining my change. Oh, yeah, hey, we're already up to these super high numbers. This one seems way better. Like has a greedy heuristic because so the all next plan sorter was actually sorting the opposite way I wanted. It was sorting low first, but this all next plan is picking the best valve first. So we got 2571 off the bat, which is still better than this one has ever done. We're gonna try it. I wonder if we're still not there. Yeah, so what I'm gonna do is we're only at 45,000. I'm gonna kill the first one. I'm gonna let the second one run. My computer, for the first time ever since I bought this M1 Mac, is actually spinning up the fan. So I'm doing it well. All right, I'm gonna kill the recording for now, and I'll hook it up later. I'm gonna let this run. I think it'll only take an hour or two. So I think finally we have a possible solution. We just gotta let it go. And this recording is actually zapping into the speed of this thing. So we'll see what happens. Thanks for being here along the journey. See you guys next time. Hey, I just had another idea right before I was going to quit, so I decided to restart the recording and try again. So I'm going to optimize this further. Instead of just returning all of the pick me and the pick elephant, like picking a new plan for both of us, I'm going to only pick the one that has the less time unless it's already complete. So plans 1, plan 0, sorry. If meet time is less than L time and is not complete, then we just return, or actually we call this times. Then return So this is kind of in the greedy vein. Yeah, we still haven't gotten the 2500s. $2,554. Still not up to 2,571. They'll still all generate all possibles, you know? It's just that we're calling all next plans a little bit more, but we're doing it a little bit smarter, so. Okay. All right, we'll let these run. See you guys. Hey, welcome back. Yeah, so it was about 3 hours after I kicked off this job to run. You can see it's processed 1.3 billion items. The thing that it's running, I actually probably kicked this off. This was the last one I kicked off, and it has the most optimistic, greedy algorithm where it sorts its next plan based on the possible score increase, and it generates plans for either me or the elephant based on which one has the most to gain. And it doesn't do that completely. I suppose combining both of these would be best, but yeah, so it does these systems. So that is what I kicked off. In about 2 hours, it came up with this number 2723 with these two systems. And actually, you look at this 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So it gets 12 of the 14 possible vowels. Anyway, so I tried this number and I got the right answer. So which means this is the correct outcome. Overall, this problem really has been the toughest of all the advents that I've done so far this year. Last year, I did have one that made me go like a whole day where I thought about it for a bunch. So this is totally normal for Advent to have a 1 or 2 of these problems, so I just realized that my camera has fallen down and is totally black. So hold on 1 second. Okay, we're back. Yeah. All right. Yeah, so I'm here again. It's so funny. Yeah, I'm a bit discombobulated because of how difficult this problem was, but I'm really happy that we solved it without going and looking at other solutions, that we iterated and iterated and iterated. If we started back at the beginning, our first try was thinking about like an iterating valve state per step. And that actually ended up solving problem 1, as long as we got this very important merge method where we merged different valve states back together and chose the best. That did not even nearly hold up for valve state 2 for problem 2. So we ended up going to a planning method where we talked about plans instead of, which is a much smaller space than total iteration paths, because instead of 58 nodes, you only have to deal with 14 nodes. So we calculated a bunch of shortest paths. So we wrote our own shortest paths algorithm without looking up how to do it. Awesome. Good that we did that. And then we started part 2 by iterating over all possible plans and filtering them for feasible ones and then maximizing that. And that was just not nearly a feasible option. So then we started picking, I guess that one we left running all day, didn't return. So we came back and this evening, and I tried a greedy solution, which didn't work, but it gave us a bunch of ideas on how to pick greedy-ish plans that are, so we have a smaller plan space than all possible plans. And that's how we came upon this Allnex plan business in a plans generator that did it smartly. And then we eventually optimized that to generate better plans up front. And then when I left it running for after 2 hours, it generated the best plan. Definitely not my best solution, but hey, sometimes this is how it goes. So really appreciate you guys. If you watched this whole thing, like, I'm going to release the full one. And if you want to just leave it on in the background and listen to me hem and haw, you can. And I'm going to release also like a more compressed version of this that you can kind of see the results. But I got to do some editing to do that. So it's been fun solving all these for you guys, and I hope you enjoy it. So see you guys next time.